we now discuss the solutions of two problems from the section Group Theory that has appeared in the TS set examination held in 2019 and 2023. And the problems are related to general linear groups and special linear groups. In this lecture, we give the overview of the concepts of GLNF and SLNF and discuss the particular cases and then solve the problems. These problems and the notions are relevant to all the aspirants of junior lecturer, degree lecturer, TS set, AP set and NET also. We first discuss about GL2, P and SL2, P. What are these? The concepts go like this. Let G be the group of 2 by 2 matrices A, B, C, D, first row A, B, second row C, D, where A, B, C, D are integers modulo P, where P is a prime number. This is G is the group of all 2 by 2 matrices A, B, C, D, where A, B, C, D are coming from ZP. Integers modulo P means ZP, which is a field, such that AD minus BC not equal to 0. That means these are non-singular matrices with the entries coming from ZP under the matrix multiplication. Agreed. Now, such a group G we take, and G is denoted by GL2, P. That means GL means, and that means this is called the general linear group of 2 by 2 non-singular matrices over ZP. That means the elements coming from the finite field of order P, where P is a prime number. Now the question is, what is the order of G? That is, what is the order of GL2P? And the order of GL2P we have, and this is the formula you have to remember. It's very important and you can use it wherever it is necessary. Modulus of GL2P is equal to P square minus 1 multiplied by P square minus P. Agreed. So GL2P denotes the group of all 2 by 2 non-singular matrices with the entries coming from ZP, a finite field of order P, where P is a prime number and it is a general linear group. That is why GL has come. Right, the order is given by this. Now we have another concept called SL2P. SL2P is the set of all those matrices A belongs to GL2P, that means the above general linear group, whose determinant is 1. So the set of all A belongs to GL2P such that determinant of A is equal to 1. So now this SL2P, it is a subgroup of GL2P and it is called the special linear group of 2 by 2 non-singular matrices of determinant 1. So that means in GL2P, go into the GL2P, catch hold of all those matrices whose determinants are 1 and put it in SL2P. And that forms a subgroup of GL2P. And it is a subgroup of GL2P and it is called special linear group of 2 by 2 non-singular matrices with the determinant 1 over ZP. That means the entries are coming from ZP. And what is the order? The order of SL2P is equal to 1 by P minus 1 multiplied by order of GL2P. the order of GL2P. So that means if you say take 1 by P minus 1 and put this P square for order of GL2P, put P square minus 1 into P square minus P, and you will get this is the answer, P into P square minus 1. So you have to remember these two formulae, very, very important. And SL2P not only subgroup of GL2P, but it is also a normal subgroup of GL2P. Right? These are the two concepts. One is GL2P and the other is SL2P and their relationship. That is SL2P is a normal subgroup of GL2P. Based on this, sometimes problems do occur in the examination. Now we now discuss a problem that has given in TS Set 2019 exam with question number 67 and question ID this one. So with this question ID it has come. What's the problem? Let G denote the group GL2 in brackets Z by 3Z. Z by 3Z means Z3. ZP where P is 3. So it's a finite field which is the group of 2 by 2 matrices. Here this word is missing. Non-singular should be there. So 2 by 2 non-singular matrices with the entries from the group Z by 3Z, that means Z3, that is ZP for P is equal to 3, which is a finite field. And the question is, what is the order of G? And we are given 4 options. Agreed. Agreed. Now, solution. Given G is GL2 Z by 3Z, that is GL2 Z by 3Z is Z3, that is ZP, where P is 3, 3 is prime, therefore Z3 is a field, GL2. And this is same as GL2, comma 3. And we have the formula for the order of GL2P is equal to P square minus 1 into P square minus P. And now order of G is equal to order of GL2, 3. So for P, 3 substitute, then you will get 3 square minus 1 into 3 square minus 3, that is 8 into 6, that is 48. So the answer is option 3. So the answer for this question is option 3. Agreed. Now let G be the group of all 2 by 2 matrices ABCD, where ABCD are from the group or from the field. They say group, but it is a field, Z by 3Z, that is Z3, that is ZP for P is equal to 3. It is a field such that AD minus BC is equal to 1. That means the determinant of the matrices is 1. Under matrix multiplication, what is the order of G? This is precisely SL. This is precisely SL23. How do we get SL23? 1 by P minus 1. P is 3. 1 by 3 minus 1 multiplied into the order of GL23. That is 1 by 3 minus 1 is 1 by 2 into 48. That is 24. Agreed. There is another question that has appeared in the TS Set 2023 with question number 67 with this question ID. Let P be a prime and let G denote the group GL2 Z by PZ, that is ZP, where P is a prime number. That is a field which is the group of 2 by 2 matrices, 2 by 2 non-singular matrix. There should be, the word non-singular should be there, it is missing, with entries from the group Z by PZ. That means the entries are coming from ZP. What is the order of G? It is the same question that is given in 2019, and where P was given to be whatever a particular value of 3, P is equal to 3 was given there. So here the general P is there. So that's the only difference. So these are the 4 options given to us, and we have P, a given prime number. Given G is equal to GL to Z by PZ. Z by PZ is same as ZP. It's a field because P is a prime. So the 2 by 2 non-singular matrices with the entries coming from ZP, and that is GL to P. So order of G is equal to order of GL to P is equal to, you have to remember this formula, P square minus 1 into P square minus P. To get the form of the options, we write P minus 1 into P plus 1 for P square minus 1. From P square minus P, P is taken common, P into P minus 1. So this is equal to P into P minus 1 into P minus 1, P minus 1 whole square into P plus 1. And to put it in the form of the options, it is same as P into 1 minus P square into P plus 1. That is precisely your option 1. So that is your option 1 is your answer. It is a damn sure easy question. Agreed. Agreed. Now, instead of P, ZP, the finite field ZP, can we put a finite, arbitrary finite field F with Q elements? That means that ZP, can we replace that finite field ZP where P is a prime? Can we replace by a finite field F with Q elements? Then can we talk about GLNF and SLNF? And obviously the answer is yes. This is a general concept. Let F be a finite field with Q elements. And from the finite field theory, Q must be a power of a prime. Agreed. Well, what do we take? F is a finite field with Q elements. And from the finite field theory, Q must be a prime power. Let G be the group of all n by n matrices. Capital A is equal to Aij n by n, where Aij belongs to the field F such that determinant of A not equal to 0 under matrix multiplication. So this time we are considering G is the group of all n by n matrices whose entries are coming from the field F such that determinant of A not equal to 0. That means they are non-singular, and that's a group under matrix multiplication. And G is denoted by GLNF. GLNF or GLNQ. So you have to remember GLNF or GLNQ, called general linear group of n by n non-singular matrices over a finite field F with Q elements. Right? So now what is the order of GLNF? The order of GLNF is same as the order of GLNQ. You have to remember the formula is Q power n minus 1 into Q power n minus Q into Q power n minus Q square, etc. Q power n minus Q to the power of n minus 1. That's the last factor. So to remember. So the order of GLNF is equal to the order of GLNQ is equal to Q to the power of n minus 1 multiplied by Q to the power of n minus Q multiplied by Q to the power of n minus Q square at the end, etc. Q to the power of n minus Q to the power of n minus 1. Now, we can also talk about SLNF. SLNF is equal to SLNQ is equal to the set of all A belongs to GLNQ whose such that determinant of A is equal to 1. So, it is a subgroup of GLNQ and it is called the special linear group of n by n non-singular matrices with the determinant 1 over the field F, that is the entries are coming from the field F. Then the order of SLNQ is equal to 1 by Q minus 1 into the order of GLNQ. That means you have to divide by the Q minus 1. divide the order of GLNQ by Q minus 1. And SLNQ is not only a subgroup of GLNQ, but it's also a normal subgroup. It's also a normal subgroup. Agreed. We go to show you an example. This example is, let G denote the group GL3 Z by 2Z. Z by 2Z means Z2. ZP, P is equal to 2. Right. And whose entries are 0 and 1, addition modulo 2 and multiplication modulo 2. Which is the group of 3 by 3, this time 3 by 3 non-singular matrices with the entries from Z by 2Z, that is Z2, under matrix multiplication. So that means this is GL32 only. What is the order? So the options are given to us, and given G is equal to GL3 Z by 2Z, GL that is equal to GL3 Z2, that is ZP, P is equal to 2. Z2 consists of 0 and 0, 1 with addition modulo 2 and multiplication modulo 2. It's a group. It is a field. It is a field. This is same as GL3, 2. Now, order of G is equal to order of GL3P, and the formula is P cube minus 1 into P cube minus P into P cube minus P square. Agreed. For P is put 2. So, order of G is equal to order of GL32 is equal to 2 cube minus 1 into 2 cube minus 2 into 2 cube minus 2 square, and that is 7, yes, 6 into 4, that is 168. The answer is option 3. So that is the detailed discussion of, anyway. So we also do order of SL32. Order of SL32 is 1 by P minus 1 or Q minus 1, that is 2 minus 1 multiplied by order of GL32. But order of this 1 by 2 minus 1 is 1 only, and order of SL32 is same as order of GL32. That means GL32 and SL32 are precisely the same groups. Agreed. So that is the detailed discussion of the solutions of the problems from the group theory, wherein we have introduced the concepts of GLNF or GLNQ or SLNF or SLNQ and their particular cases, and the two problems that have come in 2019 and 2023. I am sure that you have understood the solutions of this problem, and I wish you all the best. Thank you.